Greetings and salutations, magical chemists. Let's talk about formal charge. This is a way to identify the best possible Lewis dot structure when there's more than one valid Lewis dot structure that you can draw for a given molecule. Formal charges aren't necessarily real charges. You could call them hypothetical charges. But just like our imaginary oxidation numbers, they're charges that are assigned to each element within the compound. Now, the formal charge calculation looks complicated because you have to use a lot of words to write it, but I swear it's not that bad. So, to calculate formal charge, you just take the number of valence electrons that a neutral atom of that element would have, and then you subtract the number of lone pairs it has, and then you subtract half the number of electrons that are participating in a bond. There's good news and bad news. Good news, you don't have to show any work for this. You're allowed to just put a number. Ta-da, that's the formal charge, and we win. However, they're not going to give you this equation. You got to know it. The way you determine which Lewis dot structure is best is you look at all the different formal charges on each atom, and here's what you're looking for. First, you're looking for the smallest possible number. The best case scenario, you want your formal charges to be 0. And you want to have any negative formal charge on the most electronegative atoms. And of course, that means you would have positive formal charges on the least electronegative atoms. And just like those oxidation states, when you add up all the formal charges on every atom, they have to equal the charge on the molecule. Now, there's a quick trick you can learn that hopefully you can start to recognize when the formal charge is going to be 0 at a glance without actually having to do any math. Basically, the formal charge is going to be 0 when the atom forms the number of bonds that you think it should based on its Lewis dot structure. For example, hydrogen. Hydrogen has one single valence electron, so it should form one bond. Well, a hydrogen with one bond, formal charge is 0. Boron, of course, has 3 single electrons, so it forms 3 bonds to be stable, no lone pairs, which means when boron forming those 3 bonds, no lone pairs, has a formal charge of 0. Carbon, of course, doesn't want to have lone pairs, and it always needs to form 4 bonds. That can look like a lot of different things. It can have 4 single bonds, 2 double bonds, a triple bond and a single bond, or, any combination. But so basically, carbon with no lone pairs and 4 bonds total has a formal charge of 0. Nitrogen, which of course has a lone pair and 3 single electrons, wants to form 3 bonds. So a nitrogen with 1 lone pair and a total of 3 bonds, formal charge of 0. Just like carbon, those 3 bonds can happen in a variety of ways, but as long as that's the total, it's still going to have a formal charge of 0. Oxygen, of course, 2 lone pairs, 2 bonds. And fluorine, 3 lone pairs, 1 bond. Okay, let's go ahead and try a practice problem. We're going to go step by step on this practice problem and actually solve out the calculation, but hopefully you'll never have to do this again. This is something that is very straightforward to do in your head. Okay, when you're going to go ahead and start identifying the formal charge on a given atom within a compound, you need to start by knowing how many valence electrons it had as a neutral atom. Well, oxygen and sulfur, kind of funny, they're all in group 6, which means they all have 6 valence electrons to start. I swear this compound is not as evil as that makes it look. Okay, so now what we're going to do is we are going to subtract the number of non-bonding electrons. That just means the lone pairs, the electrons in the lone pair, I should say. Well, this first oxygen has 3 lone pairs, which means we can subtract away 6 electrons from the lone pairs. Sulfur, of course, only has 1 lone pair, so we're just going to subtract the 2. And then that other oxygen is symmetrical, so it's got the 6 lone pair electrons as well. All right, last but not least, we're going to subtract away half the bonding electrons. Well, here's the thing. Every line means 2 electrons are being shared. So if there's 1 bond, there are 2 electrons, but then we divide that by half. So in reality, which is what this means is subtract the number of bonds. So this oxygen has 1 bond, so we subtract away 1. Sulfur, of course, has 2 bonds, 1 on each side, so we have to subtract away 2. And then the last oxygen, 1 bond, we subtract away 1. So then all you do is you add together all the things in the column, and that gets you the formal charge. So you can see the oxygens each have a formal charge of -1, but the sulfur in the middle has a formal charge of +2. So this is definitely not ideal. We're trying to find things that have zero formal charge if possible, and none of these have a zero. So this one isn't looking good. Let's go ahead and try another one. Hopefully you can tell at a glance, hey, look at that happy oxygen. Has 2 lone pairs and 2 bonds just like it wants to. So hopefully you don't even have to do the work to recognize that this one has a formal charge of 0. But it's good to check, right? Because we started off with 6 valence electrons, but there were 4 electrons in lone pairs we can subtract, and then there are 2 bonds being formed. Hey, look, it is 0, just like we predicted. All right. I would like you to finish this fun and exciting column of delicious numbers. And then, when you're ready to check your answers, unpause the video. Okay, technically, you really just need these numbers at the bottom, but if you're at all confused by where the numbers are coming from, definitely show the math. Ta-da! All right. Hopefully that was fairly straightforward, and this is just something you have to internalize. You have to be able to calculate without looking back at that equation. So now the real question is, that's great, we've got all these numbers, what do we do with them? Well, we use them to figure out of these multiple valid Lewis dot structures, because any of these technically are valid. Well, which one of these structures, or 2 or 3 of these structures, best represents SO2? Hopefully you can tell that there is one that definitely does not. It is dead to us, right? It has higher formal charges. However, these last 2, they're actually completely symmetric, right? So both of the last 2 structures are equally valid and better than the first possible option. So in terms of how you would explain that, you have to identify, okay, first, they've got lower formal charges. And did you notice, so oxygen, having fewer energy levels than sulfur, is more electronegative, and it ended up with the negative. Whereas sulfur, less electronegative, ended up with a positive. So that's a good sign too. So now we just got to say that in words. If you were writing this on a free response, you would need to identify both of those reasons to fully explain and thus get full credit. Okay, so that's what formal charges are. Let's talk about a situation where they are needed. Something known as resonance structures. There are certain molecules, and SO2 is one of them, where there's more than one completely valid and awesome Lewis dot structure. Well, the crazy thing is, each one of those valid Lewis dot structures contributes to the real or observed structure. In resonance structures, it's important to recognize all the atoms are in the same place. Remember, when we were looking at SO2, the sulfur and the 2 oxygens didn't change place. So they all stay in the same relative position. It's the distribution of electrons that's different. The actual real observed structure is called a resonance hybrid. It's a hybrid between the multiple resonance forms. I've seen as many as 6 or 8 resonance forms that can possibly contribute. So there's a lot. Sometimes there's only 2. And so this real structure, the resonance hybrid, is intermediate between all the different resonance structures. Technically, all the possible dot structures are going to contribute, but the most stable ones, based on the formal charge stuff we were just doing, so we're looking for lowest formal charges, those are going to contribute more. So it's funny, just like you could take 2 different breeds of dog and make a puppy that has characteristics of both of them, yay puppies, that's exactly what's happening when you look at your resonance hybrid. What we usually do is so for instance, ozone, O3, can be represented by 2 equally valid resonance resonance structures. So we usually will draw them both, and we'll put a double-sided arrow between them. Then, when you draw the final resonance hybrid, did you notice the bond? It's not a single bond, it's not a double bond, it's like a 1.5 bond. And actually, that's exactly what they say. This one would have a 1.5 bond order, because that's its average bond order between the 2 resonance structures. Okay, so here is another example. So let's see. One thing to make sure, you may be noticing this pattern here, but the resonance structures that most often happen, they happen when you've got double or triple bonds, and the placement of the double or triple bonds changes. So many of our delicious polyatomic ions exhibit resonance. For instance, if you were trying to draw the Lewis dot structure of nitrate, well, you're always going to end up having one double bond between the nitrogen and one of the three oxygens, but then the other two oxygens end up having single bonds. So notice, there are three resonance structures. You're just basically changing the location of where you put the double bond. But that means the actual structure is an amalgamation of all three. So in this case, when you look at, and it's still just a solid line with a dotted line, when you look at them, you'll notice that the bond order on nitrate is actually 1.3. Well, 3, 3, 3, 3, 1 1/3, right? Because it's an average between one resonance structure with a double bond and two of them with single bonds. So if you're going to use formal charge, which is totally a thing you could do to look at these, well, notice the oxygen that has the double bond with the two lone pairs, that's always going to have a formal charge because that's the way it wants to be. Nitrogen, however, has lost a lone pair and formed a bond instead, so nitrogen ends up having a +1 formal charge. And then those two oxygens that have a single bond and three lone pairs all have a -1 formal charge. Why does this matter? Well, this way you can see that first, all of these resonance structures are equally valid by formal charge, and you can see that you actually can calculate the formal charge on the resonance hybrid, the real structure. They're just fractions, and it's kind of gross, but it's totally a thing. All right, I know resonance is a little weird, so we're going to practice that lot in class when I see you again. But first, we have one more video, all about isomers. I'll see you there.